Now that we have discussed what a determinant is, let's actually apply it. And we use the determinant to find the inverse of a square matrix. Now, before we do that, let's just make sure that we understand what an inverse does. When we discussed this with functions, we said, okay, well, if our function, for example, were x squared, and its inverse function were root x, we said that when we compose a function of its inverse function, we see that we are effectively inputting that function into itself. And what that does is that undoes the effect of that function. So if f of x is trying to square your argument, its inverse is taking the square root of its argument. It is undoing the effect of that function. Now, with matrices, we see that when you multiply a function by its inverse, what that should result in is what we call the identity matrix, which again is a matrix that looks effectively like it's an RREF. It's got one down its main diagonal and zeros everywhere else. So if a matrix has an inverse, if it does indeed have an inverse, we say that that matrix is invertible. Another way of describing that is non-singular. Now, if the matrix does not have an inverse, then we then call it singular. So let's talk about today, how do we find the inverse of a matrix? And we're going to start with a really basic one. We're going to start with a 2 by 2, and then we'll see what happens when we get to a more complicated 3 by 3 or even larger matrix. So for a 2 by 2, it's pretty simple. It's going to be the reciprocal of the determinant of that matrix, so 1 over the determinant of A, times, and this is going to look a little wonky at first, but we're then going to multiply it by a matrix that has these two entries here flipped around, and then simply the opposite signs of B and C. Okay, so this is another way of that being written out, right? So let's just actually try a problem with this. So let's look at a matrix here. We have a simple 2 by 2 matrix. So the first thing we're going to do is we're going to find the determinant of this matrix. So the determinant of matrix A is going to be 2 minus, and then we're going to subtract the product of -1 and -3, which is 3. So the determinant of this matrix A is equal to -1. Now, what does this inverse look like? This is going to be 1 over its determinant, -1, by, now let's look at this new matrix here. We've got 2 times 1, or 2 and 1, we're going to flip those entries. So now that's going to go 1 and 2. And then we're going to flip the signs here of -1 and -3. So that's going to be +1 and +3. Now we're going to just do scalar multiplication and multiply this value here, 1 over -1, which is just -1. And so its inverse then looks like this: -1, -2, -1, -3. And I just did that in order just so you can see that we were going down the main diagonal there, but it doesn't really matter. So we just have that. So a 2 by 2 inverse isn't too bad. 1 over the determinant, and that multiplied by this new matrix that we have, which flips around the order of A and D and flips the signs of B and C. It's kind of strange to remember all that, but it's not too bad again once you do a few of them. Now, what about when we get to a 3 by 3 matrix? And look, I'm not going to sugarcoat it. This is going to look like a bit of work because it is. But just follow along, follow the steps, and I think once you get the structure down, you'll be able to do a few more without any real difficulty. And honestly, once we do them, most of the times in practice, we'll use a graphing calculator for this. You will not need to worry about finding an inverse of a matrix larger than a 3 by 3 in this class. But let's go through the process. So the inverse of a 3 by 3 matrix involves finding, again, multiplying the reciprocal of your determinant of your matrix times something that we call the adjugate. And that's where we're going to spend the bulk of our time practicing. So let's find, first off, the determinant of our matrix here. So I'm going to go ahead and, like I said in the last video, I'm going to start with the row or column that has the most number of zeros. You could have used column 1 or row 2, it doesn't matter, but I'm just going to go with column 2. So that's going to be 2, so let's write that 2, let's just kind of zoom in here, 2 times the following. Again, I'm going to go ahead and eliminate this row and eliminate that column. And so what do you have? You have 1, this value here, this product, minus -6. So 1 minus -6, that's just 1 plus 6. So we have that there. okay? So we had that first value, and so that should just give me 14. So I'm just going to write that there. This next one, first off, note that it is subtraction. We're going to say minus, but because this value is 0, and I can cross all this stuff out, I don't have to bother finding that minor of 0. I just know that anything times 0 is 0, so I'm just going to write that there. Now, finally, I'm on to my last entry of this column, so I'm going to cross all that out. So we have plus 3, back to positive, times. We have -1 times 3, which is -3, minus -4. So -3 minus 4. Or, not sure if I said minus -4 earlier, but it should be that. So then that should give me plus 3 times -7. And if I'm not mistaken, that should give me 14 minus 21, which is -7. So there's your determinant, okay? So I'm just going to box that, even though it's not our final answer. But there's the determinant of our matrix, okay? All right, next up. Now that we have the determinant of the matrix, let's now set up something called the adjugate. And to find the adjugate, it's a couple of steps, but the first step is to find the matrix of minors. So this part might not be the most popular thing for me to say, but you know how we just found a couple of minors right now to find the determinant? We need to create an entire matrix full of those minors. So, in other words, what is the minor of 2, right? Well, we already found that. That's 1 minus -6. So 2 times 1 minus -6, which we said was going to be then, oh, excuse me, the minor itself, we don't have to multiply by the 2, we just do 1 minus -6, which was just 7. So the minor of 2 is 7. Next up, if we'd say then this term here, -1, we cross out these, cross that out, and we find the minor of -1. Well, that's 0 times 1, which is 0, minus 9. So that's just going to give me -9. Next up, let's find the minor of 4. Cross these out, and we're going to go 0 times -2, which is 0, minus 3, which is just -3. Now, me saying it out loud and articulating it may make this seem like it takes a long time, but if you just keep track of it and don't rush yourself, you actually go through it fairly efficiently. So I encourage you to pause right now and see if you can find the rest of the minors of this matrix. Well, if you've paused and you've come back, let's check our answers. You should hopefully have gotten the following values here. Okay, and I'm going to copy this because I'm going to need this in my next step. So this right here is the matrix of my minors. Now, if we move to our next step now, which is define what we call the matrix of cofactors. And all that means is we're going to apply the matrix of signs that we used earlier in the previous video to find the determinant, and we're just going to apply that here. In other words, this is a positive 7, that's fine. This next one should be a negative of a negative, so we're going to say negative of this value. And this again is positive. Negative, we're going to keep this positive, negative of this value, positive, negative, and positive. So what does all that look like? So let me keep that in a different color. So what does this matrix of cofactors look like? It was positive 7. Since we're taking a negative of a -9, that's positive 9. We're taking a positive of a -3, so we're going to keep that negative. And we're just going to go through and apply those signs. -7, -10, positive 1, -7, -6, positive 2. So this is, again, what we call our matrix of cofactors. Now, in my next step, the adjugate is going to be this matrix of cofactors transposed. So to transpose effectively means that we are going to reflect over the diagonal. In other words, what it's going to look like is that your first row is going to become your first column. Your second row is going to become your second column. Your third row is going to become your third column, and so on, right? So what that means is we're just going to flip these rows over the diagonal. So this row 1, which was 7, 9, -3, becomes my first column. This row here becomes your second column, and this row here becomes your third column. And I promise you, we are just about done, okay? Now that we have the transposed matrix of cofactors, what we're now going to do is we're then just going to multiply this here, this transposed matrix of cofactors. This is my adjugate. We're going to multiply it again by the reciprocal of our determinant, and that is our inverse matrix. So just to finish this up, what did we say our determinant was? It was -7. So we're going to say our inverse is 1 over our determinant, which was -7, times this, and I'm just going to go ahead and copy and paste this since I don't want to rewrite it again. Okay, so we're now going to multiply this by our adjugate, and once we have distributed that or done that scalar multiplication, we are done. So -1/7 times 7 should be -1. -1/7 times -7 should be +1. Again, +1. And we're just going to go through and do the rest of these. So I give you 10 over 7 and 6 over 7. It's going to kind of bother me that I went with a diagonal fraction there and kept it vertical everywhere else. We have 3 over 7, -1 over 7, -2 over 7. This, my friends, is the inverse matrix. So if your parents or your friends ask you, what is this lesson all about? You would say, oh, it's about finding the inverse of a square matrix. And we do that by multiplying the determinant reciprocal by the adjugate, which is simply the transposed matrix of cofactors. Really simple, right? I hope you got that sarcasm through the video. So the final thing that I want to just finish up with is, now that we know how to find the inverse of a matrix, what on earth do we use it for? Well, we use it to solve a system of equations using an inverse. This is just another way of solving a system. So if a matrix is invertible, then that system of linear equations is represented by this following, where A, let me write all this out. The A is going to represent our coefficient matrix. This X here is our variable matrix. And this B here is known as our constant matrix. Now, normally when we're doing this algebraically, if you saw something like 2x is equal to 6, well, from our earliest algebra stages, we know that what we would typically do, excuse me, not by 2, we would typically divide everything by 2, and then that's how you get x is equal to 3. Now, when it comes to multiplying by matrices, it's just another way of thinking about that. We can't actually divide matrices. So instead, what we do is we think about, okay, what is the inverse of multiplying by something by 2? What is the operation that is going to undo that? Well, it is multiplying something by 1/2, right? In other words, if we involve the inverse in this, this is another way of getting this coefficient here to become 1. And that's exactly what we do with a matrix. So when we're doing AX time or is equal to B, we can't divide by A. But if we involve the inverse and we say, okay, let's do A inverse times A, and then on the other side, A inverse times B, this here, as we remember discussing earlier, multiplying a matrix by its inverse gets to the identity matrix, which remember is a matrix comprised of ones down the main diagonal and everywhere else. This would be I times X. And this is how we would solve a system. This is how we would isolate that X or that variable matrix, so that our solution is just simply the following here. So as I keep saying, I think it'll be most helpful if you see this in an actual problem. So let's go ahead and do this example here so you can see kind of how this works. So we have a system. We're going to write that system as a matrix equation. So first off, let's write our coefficient matrix, which is going to be 2, -1, 4, 0, 1, 3, 3, -2, and 1. Then we're going to multiply it by our variable matrix, which means we're going to have a single column with X, Y, and Z. And all of this here is equal to our solution or our constant matrix, which is -2, -1, and 3. okay? Now, we did all the heavy lifting for this problem already. We already know what our um, inverse matrix is going to look like. Now, something that I recommend, so our inverse matrix is this matrix that we have here. Something that I recommend doing is when we're solving a system with the inverse, using the inverse, I recommend not distributing that reciprocal of the determinant just yet. Keep it in this form because it's just going to make our life easier when we do our matrix multiplication. So what I'm going to do is I'm going to go ahead and I'm going to take this here, right? This is our inverse. We just haven't distributed or multiplied by that scalar just yet. But I'm going to write this here. I'm going to say, okay, so our solution, right? Remember, x is equal to A inverse times B. So this here is my A inverse. This is my A inverse. And now let's multiply it by B. What was my B? That is this matrix here. Okay? So we're now going to multiply. So now you can see, hopefully you see why I didn't distribute that -1/7 just yet. Because it's easier to work with this multiplication here of multiplying that matrix by this matrix than it is to have this -1/7 distributed first. So what that is going to look like, and again, can we multiply this? This is a 3/2 times a 3/1. Oh, excuse me, that's a 3/3. I apologize, not a 3/2. 3/3. This can be multiplied because these values are equal. This result is going to be a 3/1 matrix. So we're going to say this is equal to the following. And I'm going to still leave that 1/7, -1/7 on the outside. For the sake of time, if you multiply these two matrices, this matrix here by this matrix, you should get -28, -26, +11. And then finally, when you distribute everything by that -1/7, you should get this as your solution. 4, 26/7, -11/7. And that is what is equal to your constant matrix, x, y, z, or your variable matrix, excuse me. So there's your answer there. So your ordered triple, we would write 4, 26/7, -11/7. So I know it was a lot, but hopefully now you have a good sense of how to solve a system using the inverse of the matrix.